In this video, I'm going to be covering 4-2, the addition rule and multiplication rule. I'm actually going to break this section up into two different videos. The first one covering the addition rule, and then the second one covering the multiplication rule of probability. So in the prior video, we talked about the basic concepts of probability. So you should be familiar with how to calculate probability, the notations of probability, and just basic definitions of what probability is, right? Probability measures the likelihood of an event occurring. And also, you have to have this down solid, just calculating probability using the formula. Okay, so let's go ahead and move into 4-2A. Again, I'm going to call this 4-2A the addition rule. So before we actually dive into the content, it's important that you understand the difference between and or. So in this situation, this problem, we have 10 students in a class, and we know certain things or characteristics about these particular students. We know their gender, and we know whether the class, right, whether they're sophomores, juniors, freshmen, sophomore, or seniors. And we also know whether they like or dislike math. So for example, this first student, she's a female, she's a sophomore, and she dislikes math. So the first question there asks, how many students are male and sophomore? So and means being both, right? How many of these students exhibit those two things? They're male and sophomores. So we know there's 5 males, but which one of those are males and sophomore? So we have this one and this one. So there's 2 students who are both male and sophomores, right? And then number 2, we have how many students are female and dislikes math. So female and dislikes math. So how many students of the 10 exhibit those 2 characteristics? All right, so female and dislikes. So we know that there's 5 females, but those who those who dislike math. So those who are both females and dislike math is this one, this one, this one, and that one. So there's 4 of them. All right, so 4 of them. Okay, so next problem says how many students likes and dislikes math. So again, one of these, it's good to view this situation as like 10 students are in a classroom and you're asking students to stand up who exhibit these characteristics, right? So for example, like male and sophomore, 2 students would be standing up because there's 2 males or 2 students who exhibit being a male and being a sophomore. Same thing with if you were to ask students to stand up if they're female and dislikes math. So 4 students would be standing up, like this student, right? And then this student, and then this student, and this student. All right. So number 3, how many students likes and dislikes math? So if you ask a classroom of students with 10 students with these characteristics, and you say stand up if you like and dislike math. Well, nobody likes and dislikes math, right? You either like or you either dislike math or you like math, but you're not in both camps. So we would say there's 0 students. And again, we're assuming that you can only like and dislike math. You don't have this love-hate relationship with math, right? Okay, number 4. So number 4, we're looking at an or situation. So number 4, we have how many students are sophomore or freshman. So an or means that it's true that you exhibit this characteristics or you exhibit this characteristics, right? Meaning one or the other. You don't have to be both. You can be one or the other. Okay, so again, imagine a classroom with these 10 students and you say stand up if you're a sophomore or a freshman. So all the sophomores will stand up. And when you say or a freshman, the freshmen would also stand up. So then we have, how many students is that? So we have 7 students. Right? 7 students would be standing up because 7 students are sophomores or freshmen. All right, and then number five says how many students are freshmen or juniors. So again, imagine a classroom, freshmen or juniors stand up, the freshmen would stand up, and the juniors would stand up. Right, so that's 5 students. And then the next one would be how many students are male or female. So males or females, stand up. So all the males will stand up when you say male, and when you include and when you say or female, all the females would stand up. So that's going to be the entire class, right? So male or female stand up, the whole entire class would stand up. Okay, and then finally, how many students are male or likes math? So you got to exhibit those 2 characteristics, or one or the other or both, right? One or the other or both. And again, when we use or in this context, in probability, it's the inclusive or, meaning male or likes or both are fine, right? You either are a male or you like math, or you are a male who likes math. You're okay as well. So this is an inclusive or. So male or likes, so there's these 5 males, they're going to stand up. And these 3 males, they like math as well, but it's not like we're going to double count them. They are already standing up. And now when you include the rest of the students who likes math, there's this one female student who likes math, so she's going to be standing up as well. So there's going to be 6 students standing up. And again, when I say inclusive or, again, I mean male or likes or both, right? So that's an inclusive or, as opposed to when the lunch lady asks you turkey or ham. She's saying turkey or ham, but not both. You can't get the turkey or the ham, right? Or maybe a different example would be like sandwich or pizza. When the lunch lady says that, she's asking you to choose one or the other, but not both. But in probability, in this class, when we say or, we're talking about inclusive or, one or the other or both. So that's what an inclusive or is. Okay, so make sure you have a strong understanding of and versus or. So first definition, a compound event. So a compound event is any event combining 2 or more simple events. So, and we use compound events is where we're going to start looking at or probabilities and whatnot. So events, and then the next definition is disjoint. So events A and B, so 2 events are disjoint or mutually exclusive. In this class, I'm going to be using the word disjoint as opposed to mutually exclusive. Those 2 terms are synonymous, but I'm going to be using the term disjoint. So events A and B are disjoint if they cannot occur at the same time. So 2 events which cannot occur at the same time are said to be disjoint. This is an elementary definition of disjoint. Later on, we're going to look at a more complicated definition. So here's a new notation for this section. So this notation is the probability of A or B occurring. So this is the probability of event A occurring or event B occurring. And again, this is an inclusive or, so A or B or both occurring. So let's take a look at this first example. So here we have 10 poker chips in a bag, colored like this with their numbers like that. So numbers 1 through 10. The first 6 are red. I'm sorry, green. There's 1 red and then there's 3 blues. So the first question says, you reach in a hand to pick a chip. Find the probability of each below. So what is the probability of that you pick 1 chip? Again, you're picking a chip, that's 1 chip. And what's the probability that it's a blue chip? So we know from the basic definition of probability, we would calculate this as the number of ways we can choose a blue chip over the total number of outcomes, right? So in this case, there's 3 ways we can choose a blue chip. That is, if we choose those 3, out of 10 possible outcomes because there's 10 different chips. So that's just going to be point or 3 over 10, or if we write this as a decimal, that's 0.3, right? And that's just basic division, right? 3 divided by 10 gives us 0.3. All right, so question B, we have the probability that it is a green chip. Again, we're picking out one chip, a chip. What is the probability that that chip is a green chip? So likewise, if the probability can be represented using a fraction, right? That would be the number of ways, the numerator would be the number of ways we can choose a green chip over the total number of outcomes. So there's 6 different ways we can choose a green chip because there's 6 green chips out of over 10 possible outcomes because there's 10 chips in the bag. And again, if we change that to a decimal, that'd be 0.6. All right, the next one, question C, we have what is the probability that that one chip that you pick out is blue or green? So what is the probability that the chip is blue or green? So now you would take a look at this and you would say, okay, blue or green, how many different ways can that happen? Well, it's got to be either a green chip or a blue chip, right? One of these. So that's going to be, let's see, that's 1, 2, 3, 4, 5, 6 green, and then plus 3, that gives me 9 over 10. So that's going to be 0.9. Okay, so you might look at this and you might start to think, okay, so the probability of blue or green, could that be, that's an or probability. Could I have just done 0.3, which is the probability of blue plus the probability of green. All right, is this equal to the probability of blue plus the probability of green? And it looks like it is, right? 0.3 plus 0.6, which is 0.9. Now, let me tell you, this is almost true. This right here, the probability of blue or is equal to the probability of blue or green is equal to the probability of B plus the probability of green is almost true. And I'll show you where it doesn't work. All right, so let's take a look at this one. So the probability that the chip is an even chip, well, how many different ways can I get an even chip? Well, let's see, that's I need to get a 2, 4, 6, 8, or 10. So that's going to be 5 different ways out of 10 possible outcomes. So that works out to be 0.5. All right, and let me go ahead and box all these answers. And now let's take a look at the last one. So what is the probability that that one chip that you select is green or even? So now, green or even. So let's think about, let's do this. So green or even. So the greens are this one, this one, this one, this one, this one, and this one. All right, and then the evens are the 2, 4, 6, 8, and 10. Okay, so let's try using that addition rule that we used, or just adding the 2 to see if that works out. Because we found the probability of green is 0.6 and the probability of even is 0.5. So let's see if that works. So is that the probability of green plus the probability of even? See if that works. The probability of green is 0.6, right? We found that out right here. And the probability of even is 0.5. Now there's a problem. So let's add this up to see what we get. So that's going to be 0.6 plus 0.5. So that gives us 1.1, which is not possible. The reason why it's not possible is because probability cannot be greater than 1. So now what happened here? So what happened here is there are chips which we double counted, or in other words, there's chips which are green or even, green and even, that we double counted. So notice how when I counted these, I counted the 6 blue and green chips, and then when I counted the evens, I double counted these other chips, right? So what happens is with the addition rule, the actual addition rule, you have to subtract those which you double count. So you have to subtract out the probability of green and even. So you have to subtract that out. So green and even would be there's 1, 2, 3 of those. So that's going to be 3 over 10, which is equal to 0.3. So now let's see if that works out. So it's going to be 0.8, right? And that's the correct answer. And let me show you an alternative way. So this is the actual definition for the addition rule. So the addition rule works for an OR probability, and the addition rule is the probability of an event. Let's call it A or B is equal to the probability of A plus the probability of B minus the probability of A and B. All right. So you can use the addition rule, which I just stated right there, or you can do the following. So an alternative to using the addition rule is just don't double count, right? So when you're working these out, if you're looking for the probability of green or even, you can just say, okay, these are the green ones, right? And then you say or even. So 2 is even, but I'm not going to double count it because I already included when I was counting the green. 4 is even, but I'm not going to double count it because I already counted. It was accounted for when I counted the green. Same thing with 6. And now just count the ones that you haven't counted, which are even. So 8 and 10. So if you just do that and not double count, you have 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be 8 over 10, right? So that's going to be 8 over 10, which is equal to 0.8. So again, a lot of times if you just don't double count, then you don't have to use the addition rule. And a lot of students prefer that. A lot of students prefer not using the addition rule, where you find the probability of the first event and then add it to the probability of the second event, and then subtract the probability of event A and B. So in this case, the event green, the probability of green and even. All right. So formally, the addition rule is the following. So the addition rule of probability is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And if we represent it with like a Venn diagram, then we have this diagram right here. So A and B is those events that are both A and B, right? Okay. So let's go ahead and look at the practice problem, and we'll come back to this idea of disjoint in a bit. Let's go ahead and take a look at these problems first. So the first question, the problem says find the probability, round answers to 4 decimal places. So we have a bag which contains 23 red marbles, 29 red jacks, 15 blue jacks, and 18 blue marbles, right? Just like the picture here depicts. Question A says if someone reached in a hand to select an item, right, one item, what is the probability of picking a jack or a blue item? So jack or blue. So the jacks are these guys right here. And the blues are these guys, but again, we're not going to double count the blue jacks. We're only going to count these which we've not counted. So if we do that, then the probability of jack and blue would be equal to, well, how many different ways can we get a blue jack? I'm sorry, it should have been or jack or blue. Then that would be the following, right? It'd be all the stuff that I circled. So that's going to be 29 plus 15, which are the jacks or blue. And then again, we're not going to double count these because we already counted them. So we're only going to include these 18 blue marbles. So in our numerator, we would get 29 plus 15 plus 18, which would be 62. That's how many different ways we can select. a jack or a blue, and then out of the total number of outcomes would be just including would be all the items, right? So all the items would be 23 plus 29 plus 15 plus 18, which is 85. As a fraction, this is the answer. And then if we want to change that to a decimal and round to 4 decimal places, we'd get the following, right? We'd go 62 divided by 85. So that'd be approximately 0.7294. All right. Let's take a look at the second one. So if someone reached in a hand to select an item, again, we're selecting one item, what is the probability of picking a marble or a blue item? So a marble or a blue item. So then, again, we're just not going to double count. So we're not going to use the addition rule. So if we're not going to double count, here's what we would do, right? So marble or blue. So how many different ways can we get a marble? Well, we can get, these guys are marbles. And then blue item. So we have these blue jacks, and we're not going to, double count the blue marbles because those were already accounted for when we were counting the marbles, right? Again, you want to imagine an OR probability, like we're gonna treat these items as if they're students in a room or something, right? People in a room, and the numerator of the probability would be the number of ways in which we can pick a blue or a marble or blue, and we would say stand up if you're a marble or blue. So all the marbles would stand up, and then the blue items, all the blue items would also stand up. But these guys were already standing up when we were counting the marbles, so it's not like you're gonna count them again, right? So all of those which are standing up would be the ones that I circle. So 23 plus 15 plus 18. So let's go ahead and add that up. So that's going to be 56 out of, again, 85, because that was 85 total. And then again, we can change this to a decimal by dividing, right? So 56 divided by 85 gives me 0.6588. Again, the instruction says to round to 4 decimal places. And that's how we got that answer. Okay, so before I go into the next part, let me just talk a little bit about disjoint events. Again, we looked at the definition up there. Disjoint events are events which cannot occur at the same time. So, for example, like examples of disjoint events is like rolling an odd number and rolling an even number. Those two events are disjointed because they can't occur at the same time. You can't get a number that is both odd or even. So you can't have an event that has those two characteristics. Whereas the following are not disjoint events. So rolling a number less than 5, rolling an even number. So those are not disjoint. Why is that? Because numbers less than 5 are 1, 2, 3, and 4. Numbers which are even are 2, 4, and 6. And those are not disjoint because they have an overlap, right? An event, there's something in that can be both of those things. Namely, 2 is in both of them and 4 is in both of those. Whereas up here, the odd numbers are 1, 3, and 5. And the even numbers are 2, 4, and 6. And there's nothing in common, right? There's nothing that can be both odd or even. All right, so that's what disjoint is. Okay, number 2 here. I'll just do one of them real quickly. Again, you have to be able to read this table. This is a two-way frequency table, and here we have drive-through order accuracy for 4 fast food chains. Assume that orders are randomly selected from those included in the table. So for example, these are orders from A, this is order from restaurant B, these are orders from restaurant C, and this is D, right? And along here, these are the orders which are accurate, these are the orders which are inaccurate or not accurate. So for example, let's take a look at like this 244, right? This 244 would be 244 orders from restaurant C which were accurate. All right. And it's also a good idea when you have a table like this, because a lot of times it's multi questions within this table. So it's always a good idea to add up the columns and the rows just to see all the totals, all the total values. So for example, if we added up the 318 plus the 38, the 356 here are the total number of orders in restaurant A, right? So if I continue that, like add up that one, so this is the total number of orders from restaurant B, and this would be what you would get if you added up these columns as well and then add these rows, right? So for example, this 973 would be the total number of orders which were accurate, and then 136 were not accurate, and this would be the D column, this would be the C, right? So to get the total number of orders, that's also a good number to get. You can add the accurate orders with the not accurate orders. So if you do the following, so if you add 973 plus 136, so the total is 1109, right? So the total is 1109. Or you could have added these four numbers. So all of orders from restaurant A, orders from restaurant B, orders from restaurant C, and then D, and then you should get the same value, the 1109, which is a total number of orders. Okay, let's take a look at the problem. So we have if one order is selected, find the probability of getting an order from restaurant A or an order from the order that is accurate. So probability of restaurant A or accurate. So we're selecting one order, and what is the probability that order is from A or it is an accurate order. So again, we can take a look at this and just ask ourselves, well, how many different ways can we get from A an order that is an A or accurate, right? So without using the addition rule, we would just take a look at the restaurant A here. These are restaurant A. Again, imagine like you have 1,109 orders in like a database, and you know, how many different ways can we select in restaurant A? All of these would stand out, and then or accurate, then all of the accurate orders here would also kind of stand out, right? And again, we're not going to include this one again when we're counting for the accurate orders because we don't want to double count, right? So if we total up those numbers, so let's see, this is 356 of the A's, and then we can add it to the other ones which we've not accounted for, the accurate orders which we've not accounted for. That would give us the total number of ways we can get A or accurate. So that's going to be 356, which is the total number of order A. And then plus 265 plus 244 plus 146, and that gives us the 1011 out of 1109. So if we work this out, we get the following. So 1011 divided by 1109, we get approximately 0.9116. Again, we're rounding to 4 decimal places. Now, if you wanted to, use the addition rule, you could. So let me work that out. So if you wanted to use the addition rule, that would be the probability of A, that the orders from restaurant A or accurate, and we know that's equal to the probability it's from restaurant A plus the probability of that the order is accurate, and then minus the probability of A and accurate. And I'm just going to abbreviate just like that. And because we totaled everything, it's pretty simple to get all those numbers, right? So the probability of A would be, there's 356 out of over 1109, plus the accurate would be the 973, so 973 over 1109 minus probability of A and accurate. So the orders which are A and accurate would be the 318 here, right? So minus 318 over 1109, right? And you can do that. So if we do that, we know that with addition and subtraction of fractions, the denominator stays the same. And all we're going to do there is just work out the numerators. So we can do the 356 plus 973 and then minus 318. And that's what we're going to get in the numerator. So the numerator would be 1101. I'm sorry, 1011. So 1011 over 1109, and which is exactly what we have here. So it's going to work out to be the same exact answer. All right, so question B, I'll let you guys work that one out independently. Please refer back to the notes where I have all the notes and answers written to check your answer. Okay, so before we end, this is the last concept. So the last concept in this section, or in this part of 4-2, would be the probability of complement formulas. So we have these formulas for complementary events. So again, complementary events are events which, well, actually, let's go back to the definition just to kind of recall. So complementary events, if I can find it, because we've taken a look at this before. So complementary events, denoted A bar, or A with a line over it, consists of all outcomes in which event A does not occur, right? So that's what complementary events are. It's also important to kind of put that side by side with the definition of disjoint. So disjoint is not here. Let's see. Right there. So events A and B are disjoint if they cannot occur at the same time. So two events are disjoint if they can't occur at the same time, whereas complementary events are... So complementary events are where consists of events. Complement of A is all the outcomes in which A does not occur. Now they sound very similar. The reason why is you're going to see that complementary events, they have to be disjoint. And we're going to add to the definition of complementary events later on. All right, so let's go ahead, go back to where we left off. So we're going to expand on the definition of complementary events. So before we looked at the basic definition of complementary events, this is a more advanced and more thorough definition. So a complementary events are disjoint events that when combined make the entire sample space. So they have two characteristics. Events are complementary if they are disjoint, and when you combine the two events, they make the entire sample space. So for example, the following are complementary. Event A is selecting a freshman, event B is selecting a non-freshman. So if you combine the freshmen with the non-freshmen, you get the entire sample space, which is the entire high school. So think about like a classroom as well. Like event, let's say the following are also complementary events, like selecting a male student and selecting a female student. So those are complementary because when you combine the male students with the female students, you get the entire class, right? Or whatever we're talking about in that case. It can be just like a room full of people. If you select if you take all the males and the females, you get the entire room. Okay, and then the formulas, we have three formulas, which is the same exact formula. These are all the same exact formula, but just written differently, right? So for example, like with this one, if we want to write this like that, all that happened there was we just subtracted the P of A over, right? So if we just subtract the P of A, which we can, right, in algebra, we do that. We subtract on one side, we have to do on the other side. So that cancels out. We get P of A complement is equal to 1 minus P of A. All right, so again, these three formulas are all the same. It's just written differently. So let's take a look at a couple of problems real fast. So we have the first one. It says find the indicated complement A certain group of women has a 0.06% rate of red-green color blindness. If a woman, so one woman, is randomly selected, what is the probability that she does not have the red-green color blindness? So if we call event A having the red-green color blindness, then A complement would be not having the red-green color blindness. So, and then we know that the probability of A is equal to 0.06%. Now we have to change that. We want to work in terms of decimals, so we have to change that percent into decimals. And we know we can do that by dividing, by dividing by 100, right? 0.0, try it again. 0.06 divided by 100, which gives us, this is actually scientific notation for 0.0006. Actually, yeah, so 0.0006. Again, this I'll talk more about scientific notation. Also refer back to your there's a video that I created on using the calculator, and it introduces you to scientific notation. But let's use like just a standard calculator. So that'd be like 0.06 divided by 100, which would give us exactly what I have here. All right, so now to figure out the probability that she does not have it, that's just P of A complement, because not having it is the complement of having it. So we can just do 1 minus 0.0006, which is going to give us the following. So we're going to go 1 minus 0.0006, and that's going to give us that. So that's going to be 0.9994. And it makes sense, and I'll explain why it makes sense. This is a very rare the red-green color blindness is very rare. This is a small probability, right? So the probability that a person does not have the red-green color blindness should be very high. It should be a very good chance of not having it. So if it's a rare disease, the probability of not having it should be good, right? Which this does indicate that it's good. Remember, probability ranges from 0 to 1, where 1 is for certain and 0 is impossible. So anything close to 0 is unlikely, very unlikely, and anything close to 1 is very likely to occur. So it is very likely that that one woman you choose does not have it, because this is such a rare disease. Okay. All right, so number 2, we have the following. So I'm going to pause the video real fast. I'm going to fill in all the numbers on the side just so you guys have that. Okay, so this was the same chart that we saw earlier with the different restaurants, and here are the totals for the columns and the rows, right? So the problem here says if one order is selected, find the probability of getting an order that is not from restaurant B. So there's a couple of ways you can do this. You can use the probability rule, the complementary formula. So that is the probability of not B would be like B complement. And we know that's equal to the probability of 1. That's equal to 1 minus the probability of B, right? That's just restating this right here. All right, and then so we would get the following. That would be the probability of B. So the probability that a restaurant is from, the order is from restaurant B would be, well, let's see, there's 319 restaurants from, or orders from restaurant B over 1109, right? So we can just punch that into the calculator, see what we get. So we can do the following. We can do 319 divided by 1109, and then we can do 1 minus. And the cool thing about this calculator is you can just press up to highlight that value, press enter to paste. So that's sort of like the copy and paste of the calculator. Press enter, and we get approximately 0.7124. Okay, so that's one way to do it. You can use a complementary formula. And I want you guys to be comfortable with using the complementary formulas, just because later on in the semester you're going to be forced to use it. In this problem, you can work around that without using it, right? So if all you did was figure out that not B would be everything else that's not included in B, so almost like as if like you just ignore the B's and you look at, okay, so not B's are the A's, the C's, and the D's, right? The orders from A, C, and D, and you can just combine them up. You can combine them like this. So the numerator would be 356 plus 274 plus 160. So those are the not B's, right? So that's going to be 790 over 1109. So 790 divided by 1109. And you would get the same exact answer as how we got it from using the complementary formula. And again, like for a problem like this, you can do it directly like this as opposed to using complementary formula. But again, please feel comfortable. Get comfortable with using the complementary formulas, because later on you're going to have to use this. Later on there are problems where you can't do it directly. All right, so I'm going to end that video there. The next video is going to cover the multiplication rule. Just a quick, another quick thing. When we think addition rule, you want to think OR probabilities. So the addition rule is OR probabilities. Let me just kind of put that in quotations here. For a single trial, and it's using a single trial. So picking a item. And the multiplication rule is something we're going to refer that to as AND probabilities in multiple trials. So in the next video, I'll talk about that in more detail.